The last part of this lecture, I want to explain to you why all of these parameters are optimal. So let's see. Message, transmission, entanglement. So the message for teleportation is 1 qubit. And you turn it into 2 classical bits, which maybe I should call C bits. And you need 1 EPR pair. And for superdense coding, the message is 2 C bits. You need 1 qubit and 1 EPR pair. So can you do better? What would happen what would go wrong if you could encode 5 qubits, no, 5 C bits, 5 classical bits by 2 qubits. Well, I mean, so here, think about this. You can take 1 qubit to 2 classical bits, and then you can re-encode them, 2 classical bits with 1 qubit. And so if you first apply superdense coding and then teleportation, you actually haven't done anything. You're sending 2 classical bits using 2 classical bits. But what would happen if you could do better? Well, what would happen is Alice could first take her 5 classical bits, and then using some number of EPR pairs, she could code them into, here we go, 2 qubits, or 2, EPR pairs, sorry. Five C bits, so 2 qubits. 5 C bits. There. So, but look, she could then go ahead and take these 2 qubits and apply teleportation, teleportation to them. And so, 2 qubits. So Alice turns the 5 classical bits into 2 qubits, but instead of sending these 2 qubits to Bob, she takes them and turns them into 4 classical bits. Again, using more EPR pairs. I guess in this case, this is just standard teleportation, so it's 2 EPR pairs. And now, Bob gets these 4 C classical bits. He turns them back into 2 qubits. And then he takes these 2 qubits and turns them back into 5 classical bits. So now you see that we've taken 5 classical bits and sent them using 4 classical bits. And you think there has to be something wrong there. And indeed, there is. If you could do this, you could communicate faster than light. Actually, I think this is probably enough to convince you that This is impossible because you could take n classical bits, turn them into 4/5 n classical bits, and repeat this until you turn them into 4 classical bits, and then set them over the wire so you can encode any number of classical bits in 4 classical bits. If you could do better than this ratio 1/2 for teleportation and 2 for superdense coding. But actually, if you can send 5 classical bits with 4 classical bits, you can communicate faster than light. And now I want to, let's say, suppose you could take 10 classical bits and code them in 2 classical bits, 4 classical bits, okay, this, I actually just realized this uses something about quantum protocols that we haven't really explained yet. So I won't, I'll just give the basic idea. So let's map a 0 to one specific range of 10 bits, and a 1 to another specific thing of 10 bits. And each of these gets mapped into, okay. And so send them using 4 bits. So what happens is Bob just guesses the 4 bits. There's only 16 possibilities. And then he pretends, using these 4 bits, to decode, to decode Alice's code with all possible, for all possible values of these 4 bits. Well, only one of them, there are only 2 possible values of Alice's code. And if you take 4 bits and try to decode it, it's very unlikely that it will give you the wrong one for any of these 16 values. So that means you know which message Alice has sent. Okay, so in reality, it's much more complicated than that, because you need to make sure that you can try all of these things using the quantum operations that you have to do on your end. And that's, and proving that requires some information about quantum algorithms that we haven't gotten to. Okay, so where were we? Well, we showed that this was optimal. We showed that this is optimal. Now I want to say that 1 EPR pair is optimal for teleporting 1 qubit. So suppose 1 EPR pair. Suppose you could teleport 2 qubits with 1 EPR pair. With 1 EPR pair. Well, what could Alice do? Alice could take 2 EPR pairs encode, well, teleport the first qubit in each to Bob, qubit in each to Bob. And she destroys one EPR pair doing this, but now Alice and Bob have 2 EPR pairs. So then Alice could take 4 EPR pairs, and with her 2 EPR pairs, she could teleport the first qubit in each of these 4 EPR pairs to Bob. And then Alice has destroyed her 2 EPR pairs, but now Alice and Bob have 4 EPR pairs. So they can keep on doing this and generate as many EPR pairs as they want, which again, you know, has to be a contradiction because you cannot send quantum information over a regular telephone line. So that shows that this, and this are all optimal. So this is optimal too, but it requires Holevo's theorem. It requires the fact that if you have 2 qubits, you cannot encode more than 2 classical bits. Or rather, if you have less than 1 EPR pair and 1 qubit, that's fewer than 2 qubits, and it requires 2 qubits to encode 2 classical bits. So if you could do better than this, you would break Holevo's theorem that says 1 qubit can only encode 1 classical bit, which we're not going to get to this term, but which if you take Ike's advanced quantum information class, I forget what it's called, he will cover it. Okay.